Okay, let's move on with our chapter about zeolites. We, in the last class, looked at how we can classify zeolites. I wanted to add a few more things to that. So a lot of properties of zeolites derive from the pore sizes. Therefore, we distinguish between so-called small pore zeolites, medium pore zeolites, and large pore zeolites. So when we have small pore zeolites, then we have windows of typically 4 to 8 membered rings and window diameters smaller than 0.5 nanometers. So examples for that are sodalite, that's the smallest pore zeolite known with only a window diameter of 0.26 nanometers, or LTA, where the window diameter is 0.41. So a property of these zeolites are that they only accommodate very small molecules. So for zeolite, actually only water is small enough to enter. For LTA, you can also have linear hydrocarbons enter as primary alcohols and primary amines as well, but any branched molecules cannot enter, and we will later on see how we can use that property actually for separation. So then we have so-called medium pore zeolites. So they typically have windows of 10 membered rings, and the pore sizes are between 0.5 and 0.7 nanometers. So MFI, for instance, is an example. So these zeolites cannot only accommodate linear hydrocarbons, but also larger branched organic molecules. So when we have windows from rings larger than 10 membered rings, then we have pore entrances that are typically larger than 0.7 nanometers. And in such large pore zeolites, we then have very little selectivity for the uptake of organic molecules, but we have very good mass transport properties. And that's a property that has found applications in petroleum cracking. We will discuss that application in a moment. So although the channel dimensionality is important, so we distinguish between so-called fibrous channels, lamellar channels, and three-dimensional channels. Okay, so this was just a brief addition to the classification of pore systems. Now let us move over from the structural properties of zeolites to the physical properties of zeolites. So one important property is the ion exchange property. So the ion exchange property results from the fact that in zeolites, we typically have aluminum incorporated in the zeolite structure. So the aluminum carries a negative charge. Therefore, we have countercations in the pores. And these cations are small enough so that they can be exchanged within these pores by other ions. So this is a result of the porosity of the zeolites in the large pore windows. So the metal ions can be exchanged by other metal ions, but they can also be exchanged just by protons. And in this case, we have so-called acidic zeolites. So now you have a great variability to tune these properties, because we can continuously vary the silicon-aluminum ratio. Okay, so when the silicon to aluminum ratio is high, okay, then we do not have very many negative charges in the framework. So we call these silicas high silicas. When we have a low silicon to aluminum ratio, then we have low silicas. Okay, however, remember that the Löwenstein rule holds. That means that the ratio can never be lower than 1:1. Okay, so this is a way to tune the ion exchange capacity. So for low silicas, you typically have high ion exchange capacity because you have more cations that need to counterbalance the anionic charges in the framework. When you have high silicon to aluminum ratio, then you have low ion exchange capacity because you have a smaller amount of countercations in the pores. Okay, so by tuning the silicon to aluminum ratio, you can also tune other properties. So for instance, the hydrophobicity. Okay, so the more counter ions we have in the pores, the more hydrophilic these pores become, because the more ionic interactions we have, namely the ionic interactions between the countercations and the negative charges within the pore walls. By continuously tuning the silicon to aluminum ratio, we can adjust the hydrophobicity of the pores. Okay, so the ion exchange properties of zeolites are highly useful. So one important application is in water softness. To soften water, here's a brief review on the hardness of water. So we distinguish between the so-called temporary hardness of water and the permanent hardness of water. So the temporary hardness of water results from the presence of calcium and magnesium bicarbonate. So these compounds have the property, when we heat them or in aqueous solution, that they become thermally unstable and release CO2 and water, and we form calcium carbonate and magnesium carbonate. And these two are not soluble in water, so they can actually deposit on hot surfaces that are in contact with water. So for instance, that is a problem in water heaters. When you heat water in water heaters, and that water has a high temporary hardness, and over the time you will deposit scale on that water heater because of these two reactions happening. So in addition to that, you can also have permanent hardness of water. The permanent hardness results from the presence of calcium sulfate in water. So the solubility of calcium sulfate in water decreases with increasing temperature. So again, when your water is in contact with a hot surface in a water heater, for example, then you actually deposit calcium sulfate on that surface in the form of scale. So for these reasons, it's useful to soften the water, and you can use zeolites for that. And one zeolite which is commonly used for that application is the zeolite A, which has the LTA structure. Okay, and it's in original form, it is sodium ions as counter ions in the framework. But when the zeolite comes in contact with calcium ions dissolved in water, then ion exchange happens. Okay, so the calcium ions go into the pores, and the sodium ions are getting released into the water. Okay, so the zeolite has a higher affinity for calcium 2+ than for sodium+, simply because of electrostatic arguments. Okay, so the calcium 2+ has a higher positive charge, therefore the electrostatic forces between the calcium 2+ and the zeolite are stronger, therefore the zeolite has a selectivity for calcium 2+ over sodium+. Okay, so zeolites are also often used in detergents because the hardness of water actually leads to a so-called scum, and that's nothing else but a precipitation reaction between anionic surfactants, and calcium plus and magnesium 2 plus. So in the presence of the zeolite, well, this scum forming doesn't happen anymore, just because again the zeolite exchanges the sodium plus ion for the calcium plus ions. All right, so the zeolite A is not the only zeolite which is used for ion exchange. Also other zeolite structures can be used, MAP or the GRS structures of zeolites are beneficial over phosphates simply because they're inorganic substances that are biologically inert. Also, phosphates can be used as water softeners because phosphate also precipitate with calcium and magnesium 2 plus, but phosphate is not that environmentally friendly because it is fertilizing, so it can actually promote algae growth. All right, so you can use the ion exchange properties of zeolites also for other applications such as water desalination. So for instance, when you have barium and silver ions as counter ions in the pores, then these barium ions can form a precipitated form of barium sulfate when in contact with, for instance, sulfate ions in the water, carbonate ions in the water, and chloride ions in the water, as well as other halogenide ions in water, get precipitated as silver chloride. Okay, so in this case, you do not just ion exchange, and when you substitute one ion by another ion in the water, you really remove the ions completely from the water due to the insolubility of these ionic compounds here. You can also free nuclear waste from certain ions. So for instance, cesium-137 is a common, product of radioactive decay in nuclear waste. So some zeolites have a specific affinity for cesium. For instance, clinoptilonide with the HAU structure in its sodium form can effectively exchange sodium plus by cesium plus, thereby removing cesium plus from aqueous solution, because the cesium plus has a higher affinity, fits better into the pores of the HEU structure in comparison to sodium. So this way of freeing water from nuclear waste was heavily used in the Chernobyl and the 3 Mile Island disasters. All right. Then another important application of zeolites are as dehydrating agents. In particular, small pore zeolites like zeolite A are suitable for that because they allow only water to enter the pores, but any other molecules cannot enter the pores. So therefore, such zeolites are good dehydrating agents if you want to, for example, dry an organic solvent. Okay, then your organic molecules are not allowed to enter the pores, but your water molecules are allowed to enter the pores. Now the pores have a high affinity for that water, therefore your organic solvent gets dehydrated. Why do zeolites have a high affinity for water? That is because they contain the counter anions in the pores, and these counteranions can coordinate water to them, so they form a hydration sphere. Okay, so at high temperature, you can actually remove that water, okay, and that produces free coordination sites. Okay, and these free coordination sites have a high affinity for water, so that at lower temperature, in the presence of water, the metal hydrate again forms. All right. Another important property is to use zeolites as adsorbents for organic molecules for the purpose of separating mixtures of organic molecules. So here you use the larger pore zeolites that cannot only accommodate water, but also larger organic molecules. So this property has been originally discovered in 1932 when it was found that chabazite with a CHA structure adsorbs methanol and formic acid, but not benzene in other larger molecules. And since then, this property zeolite has been explored widely to separate organic molecules. So there are many ways to fine-tune that selectivity through fine-tuning the zeolite pore structure. And one method is to fine-tune the pore structure by ion exchange, because the ions within the pores also influence what is the actual space available within the pores. Okay, so for instance, calcium zeolite A has a larger effective aperture compared to sodium zeolite A. Okay, so that is simply because a calcium 2 plus ion is somewhat smaller than a sodium plus ion because of its higher positive charge, and we need less many calcium ions than sodium ions in order to counterbalance the negative charges within the zeolite framework, due to the fact that calcium has a higher positive charge than sodium. Okay, so now you can continuously exchange sodium by calcium, and therefore you can continuously tune, okay, the effective aperture. And you can optimize the aperture for a particular separation. Okay, so for instance, when you exchange 1/3 of the sodium atoms by sodium ions by calcium ions, then the uptake of straight chain alkanes is allowed still, while branched alkanes are being excluded. Okay. So here you see another example. You can use this principle also for the separation of heptane and propane, for instance. So you see here again on the x-axis how many sodium ions are replaced by calcium ions in the unit cell. And here you see the number of molecules that can be in that unit cell for a particular sodium content. Okay, now you see that as the number of calcium ions increases, okay, the pores all of a sudden allow the uptake of propane, okay, but not yet the uptake of heptane, okay. But when you continue to exchange sodium by calcium, then you free even more pore space. And when you have about 3 sodium ions in a unit cell, then also the uptake of heptane is allowed. So if you wanted to separate propane from heptane, well, you would choose your sodium content, okay, or your sodium ions, the number of replaced sodium ions, probably of around 2, okay, because then propane is allowed to go into the pores while heptane is not allowed to go into the pores. Okay, so this kind of property has many applications. So for instance, you can separate long chain carbons for the manufacture of biodegradable detergents, or you can upgrade gasoline, so you can remove short chain linear hydrocarbons from branched ones that produce knocking in the engines. Okay, also the temperature can be used to fine tune the pores because of thermal expansion and, well, the vibration of the zeolite lattice. So for instance, calcium zeolite A absorbs oxygen at minus 196 degrees Celsius, but not nitrogen. Okay, so the oxygen is a little bit smaller than nitrogen, but only a tiny little bit. And that calcium zeolite at this temperature has pore sizes that are exactly suitable in order to allow oxygen to enter, but not nitrogen. However, when you increase the temperature, then because of thermal expansion and increased thermal vibrations of the O2 ions, O2 minus ions in the window, also nitrogen can be taken up and the selectivity is being lost. Okay, you see here that you can also use temperature in order to fine-tune the pore structure and achieve selectivity. Okay, so applications for that are, for instance, the purification of nitrogen by removing oxygen. Also, you can purify argon, which is also a larger gas relative to oxygen. Okay, so another interesting method to fine-tune the pore openings is the change of the aluminum to silicon ratio. So the aluminum oxygen and the and the silicon oxygen bond lengths are not exactly equal. Okay, so in fact, increase of the silicon content, okay, will lead to slight increase of the unit cell and the pore size, just because the silicon oxygen bonds are slightly longer than the silicon aluminum bonds. Okay. In addition to that, of course, the aluminum content determines how many counter ions you need in the pores. Okay, and the number of counter ions in the pores determines how many free space you have left in the pores. Okay, and last but not least, and I mentioned this before, is you can also tune the hydrophobicity and the hydrophilicity of a zeolite pore this way, and that can be important when you want to separate a more hydrophilic compound from a more hydrophobic compound. So molecules of different polarity. Okay. So these are just a few examples that show how you can use zeolites for separation applications. Okay, then another very important application of zeolites is catalysis. And much of zeolite catalysis is acid catalysis. And the acidic properties of zeolites result when you exchange the countercations in the pores by protons. Okay, whereby again you can determine the number of the protons in the pores simply by the silicon to aluminum ratio. So the more aluminum, the more protons you have. However, the more aluminum, also the weaker the acidity of the protons. So high silicas typically have few protons, but these protons are more acidic. And the low silicas, they have more protons, but these protons are less acidic. So where are these protons? So the Bernstein acid sites are actually located in between on the silicon-oxygen-silicon bridges. Okay, so the aluminum formally carries a negative charge. Therefore, the hydrogen plus tries to come as close as possible to the aluminum, but it cannot coordinate to the aluminum directly, so it coordinates to the oxygen next to the aluminum. Okay. In another view, we can also say that, well, the electronegativity difference between oxygen and aluminum is greater than the electronegativity difference between oxygen and silicon. Therefore, this bond here will be more polar than this bond here. So this oxygen here will actually be more basic in comparison to an oxygen that bridges two silicon atoms. Okay, therefore the H plus ions will coordinate preferentially to the oxide ions that are part of an aluminum oxygen silicon bridge and not of a silicon oxygen silicon bridge. Okay, so in addition to these Bernstein acid sites, we also know Lewis acid sites, and these Lewis acid sites are generated when zeolites are heated, because an aluminum oxygen silicon bridge can break. Okay, so in this case, well, tri-coordinate aluminum is being created, and that tri-coordinate aluminum is Lewis acidic. Okay, at very high temperatures, 550 degrees, you can also expel aluminum species from the framework into the pores, and these species are then even more Lewis acidic. They're also called true Lewis acid sites, because they are they're much more acidic than these Lewis acid sites, which are still part of the framework. All right, so you can do much catalysis with these acidic zeolites because the acidity provides the reactivity in order to convert hydrocarbons in a catalytic fashion. And now you can combine this reactivity with the shape selectivity of zeolites, okay, which zeolites have due to their pore sizes. So we know different types of shape selectivity of zeolites and zeolite catalysis. So one is called the reactant selectivity. So as the name says, when we have reactant selectivity, then one reactant of a reactant mixture is allowed to enter the zeolite pores, where it's catalytically transformed into the products. So for example, you may have a mixture of linear and branched alkanes, okay? And the branched alkanes are more bulky than the linear alkanes. So the branched alkanes cannot enter, but the linear ones can, and the carbon-carbon bonds are, well, cleaved in on the catalytically active acid sites to form smaller hydrocarbon fragments. Okay. All right. So here are two concrete examples for reactant selectivity that are applied in practice. So this example is the dehydration of 1-butanol and 2-butanol over calcium zeolite A and calcium zeolite X respectively. So calcium zeolite X is not reactant selective, but calcium zeolite A is, simply because of the different pore sizes. So zeolite A is smaller pore sizes than zeolite X. So here you see the 1-butanol, and here you see the 2-butanol, and the dehydration of the 1-butanol would lead to this 1-butene, and the dehydration of this 2-butanol would produce 2-butene. Okay. So now, assuming that you use zeolite A, you can selectively convert 1-butanol to 1-butene without reacting the 2-butanol at all. Okay, while zeolite X does not have that property. So you see that here on this diagram shown. So here you see 4 different curves. Okay, you see here on the y-axis the percentage of conversion of the reactants into the products. You see here on the x-axis just the temperature. So here on curve A, we have 1-butanol on calcium zeolite X, and you see that above a certain temperature, we are getting a high conversion of 1-butanol into 1-butene. Okay. However, we see that 2-butanol gets also transformed into the dehydrated product. Just we need slightly higher temperatures in order to do that. So there's very, very little selectivity of the zeolite X for these 2 reactants. But if we use calcium zeolite A, which is smaller pores, then you can see, and that is shown here in C, that the linear alcohol can still enter the pores. Okay, so above 200 degrees, you see that we are getting significant conversion into the product, while for the 2-butanol, you see nothing happens at all. Okay, there's practically zero conversion up to a temperature of 300 degrees Celsius, and that's because reactant selectivity, so the more bulky 2-butanol molecules cannot enter the pores. All right. So in addition to product selectivity, reactant selectivity, we know product selectivity. So in this case, all the reactants are allowed to enter, but only one of the products that can form within the pores can leave the pores. Okay, and because of that, the reaction equilibrium is selectively driven to the right side for one of the products, hence the name product selectivity. So here you have one example for that. So here you have methanol and toluene. So both molecules can enter here our zeolite pores, and they can react with each other so that the toluene gets methylated. Okay, now it can get methylated in various positions. It can get methylated in the ortho position, in the meta position, and in the para position. And all these reactions can happen within the zeolite pore. Okay, but only the para product has actually the right shape to leave the pore. Okay, therefore, by selectively removing the para product from the chemical equilibrium, we drive the chemical equilibrium to the right side, and the para product forms in a high yield. Okay. So that molecule here is 1,4-xylene, And the zeolite that we're using here is typically ZSM5, which has an MFI structure, and typically that ZSM5 is also impregnated with phosphoric acid in order to enhance the reactivity. So that 1,4-xylene is important industrial chemistry. Most of it is used for the production of terephthalic acid, which is the starting material for polyester fibers. So we react the terephthalic acid with alcohols to make polyester fibers such as terylene, okay? And the 1,4-xylene is produced practically exclusively because the diffusion of 1,4-xylene is 1,000 times faster than that of the other products, okay? We are meaning here 1,000 times faster diffusion out of the pores, resulting in product selectivity. Okay, so there are other examples. You can also use ZSM5 as a product selective catalyst for the production of ethyl benzene from benzene and ethane. So in principle, the benzene could be ethylated not only one time, but multiple times. Multiple ethylations would be possible, but these products would then be too bulky in order to leave the ZSM5. Okay, therefore, ethyl benzene is being formed in a high yield. So that ethyl benzene is an important precursor for styrene, which is then an important precursor for other things, for instance, for example, polystyrene, styrofoam products and things like that. Okay, a third example is the methanol to gasoline process, which also uses ZSM5. So in this case, you react methanol to form methyl ether, which then can be further transformed to C2 to C5 alkanes, so they can leave the pores, while higher molecular weight alkenes cannot leave the pore anymore. And then these alkenes can be hydrogenated in a subsequent step to alkenes, cycloalkanes and aromatics. Okay, so finally, we have the so-called restricted transition state selectivity. And in this case, we have neither reactant selectivity nor do we have product selectivity. Rather than the shape of the possible intermediates formed determine what product can form. Okay, because only one of several possible intermediates can form, because only one of them fits well into the pores, while the other ones do not fit well into the pores. So for instance, as illustrated here in this example, we can transmethylate 1,3-methylbenzene, okay? So we basically transfer one methyl group to another dimethylbenzene molecule. And this occurs through an intermediate in which we have methylene groups bridging two benzene rings. Okay. So now there is the possibility that this bridging methylene group is in meta position, okay, to the other methyl groups, as you can see here, or they can be in ortho position to the other methyl group. Okay. So now this intermediate here interferes directly with the pore walls, therefore its formation is suppressed. While this intermediate here does not interfere directly with the pore walls, therefore it can form. Because that intermediate can form, also the final product can form, and the final product is then 1,2,4-trimethylbenzene, while the 1,3,5-trimethylbenzene cannot form because of restricted transition state selectivity. All right, so another important catalytic application of zeolites is fluid catalytic cracking. This is essentially how we make petroleum fuels from crude oil, for instance, gasoline and kerosene, but also heating oil. So, so that process is done at very large scale. So in 2007, about 840,000 cubic meter of crude oil per day were converted in a fluid catalytic cracker. And these crackers use now large pore zeolites, in particular zeolite Y, okay? So that one has very large pore windows. So it can accommodate a large variety of hydrocarbons that there are in the crude oil, okay? So in this case, selectivity is not wanted. Sorry, rather than that, what's wanted is that all these molecules can diffuse fast into the pores so that the conversion into smaller hydrocarbons is achieved fast. Okay. Further, zeolite Y is highly acidic. It has 90% acidity of concentrated sulfuric acid. Therefore, it has high catalytic activity for the cracking of these large hydrocarbon molecules in the crude oil into smaller hydrocarbon molecules. Okay, so you get actually a mixture of these cracked hydrocarbons, and then you can separate them by fractional distillation into heavy gas oil, light gas oil, kerosene, gasoline, and lighter gases. So that zeolite that can perform this acid catalysis does not have infinite lifetime. Actually, over time, there's coke formation within these zeolite pores that eventually will block the pores and degrade the catalyst. Therefore, you have to regenerate that catalyst from time to time. So you do this actually with steam at 800 degrees Celsius, and then you, by this treatment, you transform the coke basically in carbon monoxide, carbon dioxide, and hydrogen, and you have your zeolite regenerated, and then you can fill it back into the reactor and continue the fluid catalytic cracking process. So this is a very large industrial scale process involving zeolites. All right, so finally, we can also do non-acid catalysis with zeolites. Not only protons can perform catalysis, also other metal cations. So for instance, lanthanide ion exchange zeolites are good catalysts because they produce a very large electrostatic field gradient in the pores. And that is because the high charge of these anions, okay? So that's a very large electric field gradient between the position in this zeolite where the trivalent cations are located in the zeolite pore walls. And because of that very large electric field gradient, molecules, hydrocarbon molecules that can enter the pores can be polarized, okay? And it can polarize and even ionize very strong bonds such as CH bonds. And that enables actually the cleavage of these CH bonds and the conversion of the hydrocarbon into another one. And actually, the first zeolite that was used for catalytic petroleum cracking was a rare earth form of a zeolite, namely zeolite X, which was only later replaced by zeolite. Why? Presumably because of cost and performance arguments. Okay, also transition metal catalysts can be introduced into the framework. In this case, you can use them not only in the ionic form as forms of cations, but you can actually reduce these cations to form actual metal particles within the zeolite pores. That works especially well with noble metal cations. Okay, so for instance, you can deposit little platinum nanoparticles in a zeolite, whereby these platinum nanoparticles then can act as a catalyst within the zeolite pores. So this way, we can, for instance, convert small straight chain hydrocarbons into branched isomers, improving the octane number of gasoline. All right, now let's do a little bit more structure after we've done so much property. Last but not least, I wanted to talk briefly about so-called zeotypes. So zeotypes are related to zeolites in the sense that they make often the same or at least similar structures, micropores structures, but now the tetrahedral centers are not aluminum and silicons, but other metal cations. Okay, so one examples are the so-called ALPO frameworks, okay, where you have the silicons replaced by aluminum and phosphorus. Okay, so aluminum has 3 valence electrons and phosphorus has 5 valence electrons. So when the ratio of aluminum to phosphorus is 1:1, then you have actually an electroneutral framework. Okay, but when you have more aluminum than phosphorus, again, your framework becomes more anionic. Okay, so these ALPOs can be either structural to zeolites. For instance, ALPO 20 makes the sodalite structure, but they can also have different structures. Okay, what you can also do is replace part of the aluminum 3+ by a metal 2+. Okay, then you have so-called MEALPOs, which are then anionic. Okay, so it's a further variation of this theme. And finally, you can have SAPOs, which in which basically not all the silicons are replaced, but some of them are left and are only partially replaced by aluminum phosphorus. And again, you can replace some of these even by metal 2+ ions. So we have here actually a wide compositional space that you can explore. Okay. So oftentimes these compounds make similar structures to zeolites or analog structures for zeolites, but there are also new structures that are known, for instance, VPI5 or clavierite. So these are examples that have extra large pores. Okay, so here the structure of VPI5, which is an alpo, and here you see clavierite. So the clavierite is unusual in the sense that you have actually here terminal OH groups. So not all oxygens are bridging, but you have actually OH groups that are dangling inside of the channels. All right. Then last but not least, a few things about zeolite synthesis. How do you make zeolites? We have learned that zeolites occur in nature as minerals, but because of their great industrial importance, they are also being synthesized. So the first laboratory zeolite, which was synthesized, was synthesized already in 1862. That was a calcium aluminum silicate. But a large increase in zeolite synthesis was then only seen when X-ray diffraction became a common characterization tool. So these zeolite structures are fairly complicated structures. They have large unit cells, and therefore they could only be well characterized after X-ray diffraction was invented. So typically, zeolites are synthesized under hydrothermal conditions in a basic medium. So up to date, it's actually not possible to rationally design zeolite pore structures. So still, there's a lot of trial and error involved together with experience and tuition, because we can have very many parameters that we can vary. Okay, so for instance, the silicon, the alumina source, of course, their ratios, then the pH and temperature ramps, synthesis time, mineralizers, stirring rates. The order of mixing can also be important, and also templates, okay, that can use as structure directing agents. So you see some of these templates here. So all these templates are organic templates. You see some of them are cationic. So many of them are cationic because you want actually to template an anionic pore, but not necessarily they have to be anionic. Also, amines can take over the role of structure directing agents. Even inorganic cations, because of their different sizes and charges, can have an influence on the pore structure that actually forms. So you synthesize these zeolites under hydrothermal conditions. That means in the presence of an aqueous solution and temperature. Typically, when you want to produce a low silica material, then relatively low temperatures are sufficient to crystallize it. The more silicon you have, the more kinetically inert the bonds become, and therefore you need more strongly hydrothermal conditions above 100 degrees Celsius. Many zeolites are metastable and not thermodynamically stable relative to quartz. Okay, so that's another important aspect to consider when synthesizing a zeolite. So you often need to apply relatively mild temperature conditions, because your zeolite is only metastable. So if you make the conditions too harsh, then actually often the activation barrier for the conversion of the zeolite into the quartz is overcome, and your zeolite synthesis actually fails. All right, so we are already 3 minutes over the time, so let us stop at this point.